Okay, let's say you're given a set of data. In this case, taking a look at the number of breeding pairs of a certain kind of bird and the percent of males that return. And you're wondering, will a straight line be a good predictor of the future? And you're asked to assess the fit of a line. This is the process you need to go to see if a line is a good fit or not. First of all, just draw your scatter plot, take a look at it. You can get some things out of that, positive or negative association. Maybe whether a line's a good fit or not, but remember your visual, it can be kind of misleading. These are the numerical summaries you need to go and write about. Go calculate the correlation. Remember, that's going to talk to you about strength and direction. Talk about what you get. Talk about your coefficient of determination. Remember, that's going to tell you the percent of the variation that got explained by the straight line. Go calculate your standard error and say what that means. Okay, this is a formula that you're going to have to use. And then finally, draw your residual plot and make sure you don't have a bad pattern. Once that's done, put it all together and say whether you think you've got a good predictor line or not. Okay? Data, and we're going, you know what? Will a straight line be a great predictor of the future? Or maybe is there a better model that we can use? If you're asked to assess the fit of a line, these are all the things you want to take a look at. Number one, visual. So I'm looking at these points. You got this graph on your paper right now. I definitely see a negative association. Okay, as the number of breeding pairs goes up, it looks like the returns are coming down. So I definitely see a negative association. As for linear, I don't know. Remember, the graphs can be deceiving. I got these points really spread out. A line might be good, might not be. That's where this further analysis comes in. First thing we want to look at is something called the correlation. Okay, I'm looking at some of your correlations on the homework. Now remember, correlation's got to be between -1 and +1. If I walk around and I see a correlation of 4, there's a problem. Okay, so remember the general rules of correlation, but also what it means. All right, so how do I find correlation? You go and you do a linear regression on these points. We use number 8. Had someone come in this morning, they were using number 4, and then we're having a heck of a time figuring out the residuals. Remember, we put the y-intercept first and the slope later. My points are in L1, L2, and there is my correlation value. It's -0.794. First, let's go ahead and write the equation of the line. It should be on your paper. So, percent of male return is equal to, our y-intercept is 157.7 minus 2.99 times breeding pairs. Now, negative slope. We were right. It does have a negative association. I can see that negative association in two different places. Number one, I see the negative slope, and we will also have the negative correlation value. Remember, they will always have the same sign. It tells us where the points are going. All right, so what does our correlation tell us? I want the 4 magic words here. Yeah, what do you got?
It's a moderate negative linear association.
And I might even have gone strong. Right? It wasn't 0.8 kind of our cutoff. So moderately strong or even strong. Negative linear association. So based on our R value, the line's not too bad. Now here's the deal on this. If any one of these break, then throw the line away. Okay, so if you can find anything up here that's not so good, okay, then you can throw it away. So far, okay. All right, R squared, the coefficient of determination. Let's remember what this thing meant. It's 63%, but what does that mean? I'm going to put the mean in here. If for every single time you say this is the number of breeding pairs, if I just guessed the mean of the percent that return, that's represented by this line. My errors, in other words, how far my guesses are, my guess is always going to be the mean here, away from the actual response variable are these. Okay? Pretty big errors. Now remember what Friday was all about. When I actually go and fit that line, how much of that goes away? Now it's actually the errors squared. Remember, it's the variation, but in general terms, it gives us an idea when I fit that line, how much black goes away. If you remember Friday, we had that in green pen. So the big fancy sentence, don't let it scare you. Yeah.
Could you also say that the least squared regression line is 60% more accurate?
No, you can't really say that because we're really just focused on the response variable. Okay? So you've got to learn the fancy sentence. And you saw in 42 last night, they gave you that big fancy sentence. But I want you to understand what that sentence means. Yeah.
So that black line, you found the mean of the percent return.
Yeah. It's just if you always ask, no matter what the breeding pair was, I just gave you the mean. Like on a test grade, you give me a minute study, I just give you what the mean of that test grade was.
Right.
That's all that's saying. It's not a bad guess, not horrible, but it's not, you're still going to have some pretty big errors if you just always give the mean. All right, so what is the sentence? But I need you to kind of understand, 63% of that goes away. Okay? The big fancy sentence, 63% of the variation. Now notice why they use the word variation. Didn't we square those errors and add them up like variance? So 63% of the total variation is explained by the least squared regression line predicting percent of male return given breeding pairs. It just means that 63% of this error went away. It's pretty good. It's a lot better than just guessing the mean. A lot of the errors we get would go away. All right, standard error. What does that mean? Well, when we do fit our line on here, the real line, unfortunately, we don't hit the exact data either with the real line. When you plug in a 28, I hope my line says 82. If it doesn't, that's a mistake. That's an error. We call it a residual. Okay, so what the standard error means is, well, okay, we have all these residuals. How much do I usually miss the real line by? How much do I actually miss the real points by in making my predictions? That's the residual. It's defined as the actual value minus what we'd have predicted. Now we have these residuals in L3, or we're going to put them there. How do we do that? It's the actual scores, the percent of males returning, those are in L2, minus, don't forget your parentheses. I saw a lot of residual plots that had all positive numbers. Okay, probably you didn't have to put the parentheses in right. Bars, statistics, equation. Don't forget to put your explanatory variable in there. Here are all of our residuals. Now, I can't find the average of these because they add up to 0. Okay, so that's why we have to have this fancy formula. Remember, these are not on your green sheets. This is the formula you have to remember. It wants us to take those residuals, square them, and add them up. SS resid. Sometimes it says SSE. It means the same thing. Sum of the squared errors. Sum of the squared residuals. Do that. One bar stat on L3. One of the things that it does is it adds them up. So on your paper right now, you should have this formula. Square root 626.9 divided by how many points there are? 9. Minus 2 is 7. This comes out to about 9 point something, 9.32. All right, Scott, you have a question?
Why do you mean not 0?
Didn't I just tell you that you add all those numbers up, they come out to 0? Does that say 0 up there? Yeah, it's really close to 0, right? Remember what that means? It's like 0.000000, scientific notation. So it's a rounding error to 0. Yeah.
Yeah, I thought that SSE, I wrote it down in my notes as the sum of y minus y hat squared.
Correct. And that's an error, right? Let's think about, I'll give you remember what a residual is the actual value minus what the least squared regression line says. So that's an error. That's one of the residuals. That's one of, that's how I would find this value. I would take the actual y value and subtract what the line says. Now, what is SS, sum of the squared residuals? Well, I take all of those errors, okay, I'm going to square them, and then add them up. That's SS residual. Okay. Yeah?
What was that last step where you divided it over
Okay, now this is determining what the average or typical error is going to be. So I square all those errors and add them up. And then remember when we found standard deviation, we divided by n minus 1 because of degrees of freedom. We have two different sets of data, that's why we divided by n minus 2. So in this particular problem, it's going to be the square root of, what was it,
26.
626? 686? 626?
26.
Divided by 7 square root. So the error comes out to 9.32. Yeah?
So that's it's telling me that the typical error from the line on average is 9.
When I predict, this is what I gotta get you to understand. When I use this line to predict, usually I'm off by about 9.3%. Your sentence should have said, because remember the response variable is in percent return. Your response variable should have said, I mean your write-up for this should have said, typically when I use the least squared regression line, my predictions are typically off by about 9.32%. Now is that big? I don't know. 82, 83, this is the percents, these are the right answers. I'm usually off by about 9%. I think that's kind of big. Now, if these numbers were in millions, would 9 be a big deal? No. So if this was like 82 million and 83 million, would the number 9 be a very big?
I was thinking 9 million.
Yeah, no, yeah. Okay? So you've got to compare it to what the response variable is. If I want to get 69%, but I got 61%, is that a big deal? Well, it's kind of a ways away. So I have an issue in this problem with the standard error. I think it's a little big. I don't want to be off on average by 9%. And finally, your residual plot. Okay, you can graph this residual plot either by the explanatory variable, L1, or the response variable, L2, comparing it to L3. Now remember, on your paper, give me the minimum maximums here, okay? But what's your analysis of this residual plot? What does this residual plot tell you? Now remember, we're looking for a pattern that makes the errors get huge. Okay, a parabola, it's not really one here. Okay. Or are the errors continuing to get bigger? Not really. Okay, so I think this is a decent random scatter. So putting it all together, visually it has a negative association. Maybe it's a line. R was pretty good, pretty strong. R squared, 63% of the variation was explained by least squared regression line. This is the one I might have a bit of a problem with. Being off by about 9 on each prediction, on average for predictions, is a little high for me. Okay, the residual plot looked fine. So it's yeah.
So what would be some of the stuff that you write for visual?
I would just say negative association could be linear, perhaps linear. That's all you can get out of visual.
Okay.
That's real quick. These are specific things I want you to talk about, and then closing it out at the end, I might say that I think the standard error is a little bit big. Yeah?
When there's a pattern, what do you say?
It's a big deal. A pattern, either a parabola shape or the errors are continuing to get bigger, that's a deal breaker. You do not want to use your line if you have a residual plot that shows a pattern.
So you just say you can't, the line can't.
The line, so if I'm assessing the fit of the line, the line's not a good fit.